This is a very important neurotransmitter. It's known for short as GABA, which stands for gamma-aminobutyric acid. It is always inhibitory wherever it occurs. Lots of projections all over the place. I don't need you to learn this, but this is a transmitter which tends to make neurons less likely to respond to excitatory influences. It has a calming down effect on the whole central nervous system, and it is very important from that point of view. If you antagonize GABA receptors in the central nervous system, you cause seizures and really damaging overactivity, overexcitation of the cerebral cortex and other areas of the brain. So its network of neurons that are tending to have an inhibitory influence on central nervous system functions are very important. That's your most important inhibitory neurotransmitter in the central nervous system. How do we use manipulating of GABA therapeutically? There are two major areas. Anticonvulsants, so treating epilepsy and other seizure disorders, and you can see straight away why that would happen. If you can increase the influence of GABA in the brain in some way, you can help to reduce the overexcitation that tends to occur when there's seizure activity. Also anxiolytics, meaning anti-anxiety drugs, again a calming effect on the central nervous system, can be therapeutic for treating anxiety disorders. And finally, last but not least, glutamate. Glutamate is also an amino acid, like GABA, but it is excitatory. Wherever you find it, it's excitatory. So it's doing the opposite to GABA, it's razzing up neurons all over the place. Equally important, but it's having the opposite effect. It's glutamate that we think is responsible for the phenomenon known as excitotoxicity. When there is too much release of glutamate, you actually get death of cells because you get overexcitation, and this seems to occur, for example, in stroke as part of the pathogenesis of stroke and the death of cells there. Certainly occurs in epilepsy. So glutamate is a very important excitatory neurotransmitter. Fiddling with glutamate function in order to produce therapeutic effects, well, there's a lot of experimental drugs. Not many of them have come through to being used clinically in humans yet, which try to block glutamate receptors in order to protect the brain during a stroke, because as I said, a large part of the damage and the death of cells that seems to occur after a period of ischemia in the brain seems to be due to massive release of glutamate, and so there's still a hope that those anti-glutamate agents might prove to be effective neuroprotective agents in stroke. And also some anticonvulsants target not GABA but glutamate, and in that case of course they would be tending to block or reduce the effectiveness of glutamate and therefore calm down the central nervous system somewhat. Okay, so that was just an introduction to the neurotransmitters. Once you have those neurotransmitters and just a brief one or two liner about each of their roles, then the pharmacology that we're going to talk about this week will fall into place much more easily, because all of our pharmacology is going to be based around those neurotransmitters and how we try to manipulate their activity either up or down.